Guten Mittag, everybody. Pretty Norsk. It's like old Icelandic, not Icelandic, Swedish and Norwegian. Yeah, they're all etymologically the same language that just have kind of drifted apart. Okay, really quickly, you can tell that this is related really closely to German and English. Midday, Mittag. Yeah. Guten Morgen. Yeah. Good morning. Like, German's not hard to learn if you speak English. Like, it's weird if you only speak English because there are still gendered and neutral nouns. But I'm sorry? You all took German. Okay. German, hit me. Eins, zwei, drei, vier, fünf, sechs, sieben, acht, neun, 10, 11, 12, 13, 14, 15, 16, 18, 19. And, oh, here you go. You remember it? 11, 12, 13, 14, 15, 20. 21. Yeah, 20 and 1. 5. Yeah, 40. All right. Are you trying to say? Why are you saying that so weird? I gotta try to draw this. Only if it has an E is it grosse? Gross. Ich habe ein Großhunde. Only if it has an E is it grosse? Mr. Holloway? 999. All right, here we go. Where do we start? Okay, thanks for the German. We start at what number? Like, we checked a bunch. Where did your homework start? Hey, Sam. Sorry, Sam.
22 and 23.
Okay, let's start at 22 then. 22 I don't think we need to do, I hope. Okay, 22, were you guys able to get through? 22, were you guys able to get 22?
I have to know. Yes. How do you say that in German?
I don't know fractions. I don't know.
I went up to
5 over 9 pi? Okay, 22 is 5 over 9 pi. Work through it or no? Okay, really quickly. We're going to go quick because I want to get started on the next one. I have a cylinder. Okay, and the radius of the cylinder is what?
The radius of the cylinder is
6 meters.
6 meters?
Oh, diameter.
Okay, so radius is 3. I'm going to call the height h right now. What am I looking, it's like, what do I know on 22?
The diameter. The diameter. The diameter is the rate of 5 centimeters.
Ooh, I don't think so. The volume is changing. dV dt stuff is flowing into this at a rate of 5 meters cubed per minute.
I couldn't figure this out.
No problem. What am I finding?
you're finding the rate at which the depth of the water is rising.
That's dH dt when what?
When it's rising.
Not just when it's rising, it's just at all. Oh, when the water is rising. Okay.
Does that mean like when it's positive?
I can pick anything. What height do you want to use? 1? Sure. Now, the reason, and I can't always do this, there's nothing about the problem that says find the height, the rate of change of the height when h is 1, but it's a cylinder. Is that if I keep pouring it in a constant speed, the height always changes at the same speed. I'll pick whatever h I want, one seems convenient. Okay. How do you find the volume of a cylinder? H. Okay. Unfortunately, if I differentiated this right now, I would get a, I guess maybe it's not really unfortunate. I would get a drdt. I will get one if I take the derivative. It doesn't really bother me. Why?
Because you know.
I know r, and I know drdt. What is drdt?
3.
drdt is? R is 3. How fast is that radius changing?
0.
0. Okay. Do you want to change it?
No.
Since this is just constant, I think it's easier if I just say, hey, check this out. It's 9 pi times h. Because the radius never changes, it's just always going to be 3 squared.
Oh, okay.
Now, if you don't want to do this, we could use product rule if you'd rather.
That's okay.
Okay? 9 pi h. Now we do what?
Derivative.
Okay, I'll do the left. dv dt.
Differentiate.
What's the constant multiple here? 9 pi. And times dh dt. What's dv dt?
It's 5.
5. And it was 5 meters cubed per minute. Over, let's see, r squared would give me meters squared. 9 pi meters squared. That becomes meters per minute. That's what my answer should be. dh dt looks like it's 5 over 9 pi meters per minute.
From 9 pi?
5 over 9 pi. Yep. If you product rule, Lily, did you product rule?
See. Yeah.
Okay.
Yeah.
You probably, maybe you did, I don't know. If you did, we're going to get the same thing.
I always forget the names of the rules, but I did.
You did multiplication stuff?
Yeah.
Okay. Yesterday, I also want to address this real quick. That was 22. The height of the water is changing at 5 over 9 pi meters per minute at any height, at all height. Okay. Yesterday, we also did something like this, right? X e to the x. We did this problem. Go ahead.
Yeah.
You said like r equals to 3
Yep,
for this problem?
I did.
Okay.
Because no matter where that is, whatever the height is, the radius is always what, German?
All
3. Yesterday, our units got weird on that problem we finished with. Do you all recall that happening?
Yeah.
Okay. Was it somebody with their work? It was on your homework, right? Or in your notes somewhere. Can you tell me what it was? Was this the original?
Yes.
It was x e to the x? Okay, and then, I don't remember exactly what it was. But we took first times the derivative of the second, we got this.
Plus.
Okay. Plus the second times the derivative of the first, so it's dx dt e to the x. We had something like this written yesterday. Order might have been different.
And then you.
We got weird on the units. Do you remember that happening? Because we were expecting units squared per time, but then one of them was cubed. It's just that I was wrong. This is a derivative. This whole thing is a derivative.
Oh, that's the problem.
Yeah, this is x is in units, and the derivative is measured how? Units per second. They were really both units per second, units squared per second. It's just for whatever reason, I was looking at this and not realizing that it was the whole derivative. Our units were right yesterday, and it was 11 e to the 10. Cool. All right, should we do 23? Okay, I have a cone, right? And it's here. What do I know?
The radius is 4 meters.
So when r is 4, or the radius of the top is 4.
Yes.
Okay.
And the height is 16 meters.
The height is 16. And I assume I'm probably filling or draining this thing.
Fill.
I'm filling it. How fast?
16. Yeah. Yeah.
Meters cubed per minute. Okay, that's a change in what? Okay, dv dt. I'm asked to find, I think it's dh dt, right? When h is 8. Okay. I'm going to leave some intentionally blank space here. Do they give you the equation? They do. Volume is 1/3 pi r squared h. I'm going to call it pi thirds r squared h. Sam, did you check in at the office? Okay. Do you have a charting note? Oh, okay. I wasn't expecting one, but okay. Somebody needed batteries yesterday?
Lily.
I have batteries. I have batteries. Okay. What's the issue if I were to take the derivative here and now?
You have
R, but the R I'm not really concerned with. The DRDT is they're really worried about. Dirty. Okay. Man. So I don't want R in there anymore. Don't want R. That's what I'm trying to get rid of. Now, luckily, it's a right circular cone, and 3 dimensions is sure hard to think in, but what's not?
2 dimensions.
2 dimensions. I'm going to cut this cone in half and just look at the middle.
Okay.
This is still 4, and this is 16.
Oh, it's a triangle.
It is a triangle, and it's a right triangle because it's a right circular cone. More so, at some point, I'm going to have a height of water in here. Not yet. Like wherever I put it, right? I could put it there. I could put it up here if I wanted to. I'm just going to call it H. And what should I call this one going across? That's the radius. What's true about these 2 triangles?
They are same shape.
Love that I heard both and the third. Okay, we'll start with that one. Same shape, different size. Or they're similar. And finally, it means they're proportional. I don't want an R in here, which means I want to be able to solve for R. Let's put R on top. We have some choices. R over what? It could be H. What else could it be?
4 over 16.
4.
It could be 4. What can it not be?
16.
It cannot be 16. What do you want? 4 is easier. Equals what over what? H over 16. Can you solve for R?
Yeah.
It's going to simplify to H over 4.
Yeah.
It's going to be 16H over what? H. Because I took radius over radius, height, little radius over big radius, little height over big height. I could have also taken little radius to little height equals big radius to big height. Same proportion. All right, let's get a better equation then. Volume then is really equal to pi thirds. What was R again? Can I just call it H squared over 16?
Yeah.
Like, you guys are cool with that? Times H, I wish I would have just skipped 2 steps. Yeah. Hindsight, right? Okay. Now I'm thinking ahead a little bit. I could do 3 times 16. I think I'm confident in my ability. I'm not going to. Pi over, I'm going to just call it 3 times 16. And H to what power? Try again? Third. Okay. This seems like a silly thing to do. Is it okay if you call it 48?
Yeah.
100%. Can you tell me what I see, why I didn't bother writing 48?
Different.
When I do the derivative, that 3 is going to come to the front. They're just going to divide out anyway. Okay. I'll take the derivative of the left. It's dv dt. And Shane will take the derivative of the right.
Pi over 16 times h squared. Wait. Oh, you didn't mind. And then you times that by dh over
Okay. Now, Shane, you're fine. You're good what you said. I just want to make sure it's clear. 3 and 3, they gone. Cool. Are we plugging in now, or are we solving and then plugging in? Doesn't matter to me at all. You plug in. What's dv dt? 16 equals, I'm going to call that pi over 16. When h is what? I'm going to call that 64 times dh dt. Will you flip your phone over, please? Thank you. What would you do next? I would simplify first, personally, because 64 over 16 is what? 4. That's 4 pi times dh dt. 16 over 4 pi? Almost. 16 over 4 pi. It does not. Where's pi? I'm okay with 4 over pi. Okay, should we play the game, or do you just want to blindly trust it? Okay.
He hates it so much.
meters per minute.
Yeah, give me context, though.
I don't remember what the problem was.
I didn't write it down.
Water is poured into the.
When the water is 8 feet deep, meters, right? Meters must be. The depth of the water, or the height of the water, whatever you want to word it, increasing or good? Increasing. How fast?
4 over pi meters per second.
I think it's per minute, but yeah.
Oh, yeah, that's fine.
4 over pi meters per minute. Could I call it 16 over 4 pi and be okay?
If you want.
Yeah, 100%. Okay, if you struggled with this problem, where did it happen? Like, where are you guys saying that these are the hardest?
When you have to
Finding the
take a different formula.
Like when you have to change your formula?
Yeah.
Okay.
Like you have to.
Or when you have multiple parts of the same thing you don't know.
Figuring out like where to put information at.
Okay.
Awesome.
Like going from the getting rid of the R is the hard part for me because I always forget.
On cone problems, especially.
Yeah, I just forget where to go.
Yeah. The good news is pretty much only cone problems that you do that with.
And they all do that.
Pretty much every cone problem, you'll use that little similar triangle trick.
Okay.
Mm-hmm.
Good to know.
Do we do more?
AP.
I love the AP problems.
You know what I did?
No?
I think I did it wrong, but kind of right.
Confusing.
Yeah.
All right. We have a.
I got the same,
I need help on too.
kind of the same number, but kind of not.
Okay. Let's take a look. On number 1, we have a spherical balloon being inflated. So 1, spherical balloon. There it is. There's this. I have a spherical balloon. It's being inflated, which means I know what in reality.
It's growing.
What's growing about it?
The volume.
The volume. Being inflated is a change in the volume inside of it. dV dt, I'm told, is 50 cubic meters per minute. Okay. I want to find the rate at which the radius of the balloon is increasing. Find, God, the rate at which the radius is increasing. dr dt. When, and I'm going to change this a little bit because it says when the diameter is 20 meters. Don't care about the diameter. When r is 10 meters. Okay, the good news about this is it's a sphere. It's no bad news. A sphere is good news because the equation for the volume of a sphere is easy. I think so. If you remember it, it's easy. It's 4/3 pi r cubed. Shouldn't be a problem.
Oh, this is easy.
Just want to highlight that real quick. The volume of a sphere is 4/3 pi r cubed. You have them all. Definitely. Okay. What do you want to do? Yeah, let's plug it in. dV dt, I'll do that side. Somebody help me with the right side.
It's 4 pi thirds times 3 r squared dr dt.
Okay, they're gone.
And then you can plug
When r is what? 10. So check it out. Here's 50. That's 400 pi. And I'm going to stop here. Why am I stopping here?
simplify it.
No. Like I don't think I'm going to do anything else.
You're good.
Not quite, but what problem is this?
AP.
AP problem.
Oh,
The
it's-
AP problems are,
Multiple choice.
so let's see, it's 5 over 400, that's 1 over 8. I see my answer. It is C.
I guessed right. Oh my god. Good no. Okay, so I did surface area. So then I got.
And it
50
worked?
No, it didn't work. So
Okay.
I got 50 over 80 pi, and then I was like, huh. Well, I think I'll just choose one that sounds right. So then I chose C, and then it's right.
That will happen. I'm going to guarantee you guys are going to wind up guessing on the AP test. Do it. Yeah, sure, whatever. Don't leave it blank.
One time on a test, I had no idea where my work was going, but I still got the right answer.
That's awesome. That works out. Okay, in the right triangle below, Anybody take a guess on this one? Did you do the problem or just blindly guess C? Quit it. Okay.
I said D though.
Let's take a look. Theta is changing at 2 radians per second. How do you write that? D theta dt. Okay, equals 2. There we go. Sure, rad per second. Okay. At what? Oh, that was also 2. Weird that they called that x. That drives me crazy. That's okay. At what rate is x changing at the instant when x equals 1? Find what? When x equals 1. Okay. Well, let's just look. I have a theta, and from this theta, how would you refer to this side?
I would refer to it as
I like the opposite. This is opposite from theta, right?
Oh, yeah.
And this is the,
Hypotenuse. Oh, so
okay, sine of theta
sin theta.
is equal to opposite x over hypotenuse 2. Okay, are we using arc sine or are we just doing sine?
I don't want to do trade, but
Sine is easier, but I don't really care what we do.
Sine.
Either would work. I'm going to use sine. What's the derivative of sine?
negative cos. No, it's not.
Just cos, theta, and then take the derivative of the inside.
1/2.
The inside,
Oh.
Theta.
d theta
Oh.
D theta
dt
Yeah.
is equal to, let's take the derivative of this side. What rule do you want to use?
Quotient.
No.
The thing you said. 1/2.
Just constant multiple, 1/2. What's the derivative of x? dx dt. I'm not really angry when I say it, but I want it to stick in your head. Okay. I'm cool with this. We're solving for theta, right?
Yeah.
What's dx dt?
dx dt. We're finding dx dt, but we know d theta dt.
Oh, we're finding dx dt. Okay, so let's see. This is going to become cosine of theta
Times 2.
times 2. I'm going to put the 2 in front because it's going to bug me otherwise. Equals, gosh, can I just multiply each side by 2 as well?
Sure.
To undo this fraction?
Sure.
dx dt, and then I'll put a 2 out in front. 2 times 2 cos theta. This would be all fine and dandy if I knew what cosine of theta was.
But
Well, hold on here. If that's 1,
then that has to be
Pythagorean triple.
1/2.
this should be root. Let's think this out.
root 3.
Is it root 3?
Probably.
It seems right. Has to be root 3.
Should we check?
It is root 3. 1 squared plus root 3 squared is 2 squared.
Okay.
Yep, we're good. It's root 3.
That's nice.
Pythagorean theorem, just in case somebody's looking at it going, what? I'm going to call this R for now. Just because it's X is what I want to call it, but it's taken. R squared plus 1 squared equals what? 4. R is equal to square root of 3. No, no problem. Okay, what's a cosine of theta when this is true then? So adjacent is root 3 over 2. Okay, so let's see, this becomes 4 times root 3 over 2 equals dx dt. It's 2 root 3, that's one of my answers, I think.
I said that, but I don't do that at all.
It is Bravo.
That's so weird. I did something. Why did you change color?
I don't know,
What did I do?
but we got it.
Oh, I did the same thing.
Related rates problems are super nice when they show up in multiple choice because they're not going to be hard enough that you have to like pick out individual little pieces. Don't guess. Don't just blindly guess. On homework and stuff, I don't know if this got stressed, but because we're going to keep doing AP problems, I need to see work. You want to do 3?
Yes.
It's like a ripple.
Ripple.
I got A.
Hey.
I guess
Do you want to do it? Yeah. Shane, I'm going to use that. I know everyone's laughing. I'm going to use that. Radius of a circle is decreasing. What is the rate of change in the area? Radius is getting smaller. The area is decreasing. All right. We already know that C and D are not even possible. Okay. Here we go. I have a circle. Here it is. Circle. Okay. The radius is decreasing at a rate of 2 inches per minute. How would you write that? dr dt is equal to -2 inches per minute. I am supposed to find how fast the area is changing. That's dA dt when what's true? When the area is 25 pi, pi inches squared. Is there a formula relating the area of a circle to its radius?
Yeah.
It's the only formula, I think. Pi r squared. dA dt. Nope. dt is what?
Wait, wouldn't it be 25 pi dA dt?
Why?
Because you know the area already, but take the derivative, so. But never mind.
Well, look, we're gonna see that there's something going on with it here. What's the derivative of this side? Okay, there is an issue though. I know 2 pi is 2 pi. I know dr dt is -2. I don't know r yet. Check it out. What's it or the area for formula? What's the area for formula? What? What's the formula for the area? Pi r squared when it's equal to what?
25 pi.
Dagon, what's r?
5.
-20 pi. The AP problems, for whatever reason, they seem like they're harder. None of these have been harder than the ones we've done so far, I don't think. You think they're what? I think they're easier too because they're multiple choice.
You get an answer that doesn't match up to any of them.
That's how I know.
That's how I.
Okay, here we go. The radius r of a sphere, they tell me we're dealing with on number 4. The radius is changing at 2 centimeters per second. dr dt. 2 centimeters per second. Okay, at the instant when r is 12, what is the rate of change in the surface area of the sphere? Well, that's change of surface area when r is equal to 12. And they even gave me this other little handy tip here. They say, hey, S is 4 pi r squared. We're almost done with this problem.
Yeah.
Like, there's nothing weird going on with it.
We know S is 12 and P.
We know R, we know dr dt, we're trying to find, we're good.
And there's no weird rules.
Nothing weird going on here at all. What do I do? Bless you. All right, that's 8 pi times 12 times 2. How do I do that multiplication? 24 times 8 seems hard. Times 2. I like 192 pi. D. Easy problem. Yeah, I tried to do 16 times 12 and then I kind of
I
panicked.
know, me too. I was like, I don't know why 6.
I'm sorry, Tristan, you asked a question.
Oh, no, I missed out.
Okay. All right. We'll come back and do more of these, I promise.
Okay.
Promise, you don't need to promise anything.
No, I do though. I'll likely give you guys some stuff to do over the break a little bit. I think 2 weeks off from calculus is pretty detrimental.
We're gonna have homework.
Yep, but I'm gonna give you enough to do like 2 problems a day.
And I'm not gonna.
I'm gonna give you a packet, yeah. Yep.
So I could do it in one day.
I like that.
Oh my gosh, there's a whole nother side of AP problems?
Oh.
All right, here we go.
And homework.
Today's stuff, honestly, I think two things in calculus are the hardest problems we'll do all year. I think related rates are hard to get used to. I don't think the math that we do in them is particularly challenging, unless you got to do some of those weird things. But like the last couple related rates we did, I hope didn't seem intimidating when we look back on them. Cones, yeah, they can be hard. Awkwardly shaped pools, yep, that can be a challenge. Circles, cubes, nice things like that, there's nothing too crazy. Okay, I think those are hard, and I think that optimization problems can be challenging as well.
What's that?
Finding mins and maxes in context. The good thing though is that I think today's stuff and the next 4.2 stuff, I think we have intuition for it already, and it's nice that we can just build up on that intuition.
I like this so much, I hope we don't move on.
You haven't done it yet.
Oh, no.
Okay.
Like last time.
Here we go. What's up? For what? Oh, okay, go ahead. Start 4.2. We're going to finish 4.2. Today, we are talking about maximum and minimum values. Maximum and minimum values. That is our focus as we go through 4.2. Now, doesn't often happen, but we get a semicolon in our title here. Specifically, we're going to talk about critical numbers. What's up? We are just starting it now for the first time. I care way more can you take the derivatives in the first lesson than can you set up related rates. Because I guarantee you get related rates on the AP problem or on the AP test, but there will be one or two of them. Whereas questions like this will be more abundant. So more important here, yeah. But again, I also think this section's easier. So that's good news, I hope. Okay, our first topic here is I want to know, how does one identify, ID, local and global extrema? Local and global extrema. Now, I'm going to give us a graph that we can use to think about this thing. When we're working on particularly global stuff, for the time being, we're going to be working on a particular interval, a closed interval. But let's consider the following graph, and our numbers don't have to be perfect.
What is ID?
Identify. All right, so we're going to get a graph on a closed interval. And let's say it does something like this. It starts at just this point, hanging out. And it does kind of like a downward opening parabola thing, goes a little bit lower than that. Then there's a sharp turn. I'm going to mark that point. It comes another upward opening parabola, gets a little bit taller, and then it comes down underneath. I'm going to make that last piece a little bit nicer so it looks more parabola-y. And then it comes down to that end point.
Oh, it's a point.
Yep. So my function might be defined for everywhere. Maybe, I don't know. But I do know, guaranteed, it's defined between these points.
Uh-huh.
Okay. Let's put a couple endpoints on here. Let's say that this was at A. The very leftmost x value was A, and the very rightmost x value was B. All right. We're going to start filling some stuff in here. Do you guys remember ever talking about extrema? Can you explain to me what an extrema is? The highest or the lowest, right? Compared to all of its neighbors. Now, as we go through, with that in mind, can you guys agree that maybe that is an extrema?
Yeah.
Okay, I'm going to go as best I can straight down. I'm going to mark that x1. Okay, and all I'm going to do is I'm going to follow along my curve. Tell me when I hit another extrema.
Right there.
Right there. Let's call that x2. All right. We're going to keep going through this thing. I assume we're going to see another one up here. Let's call that x3. Okay. Now, as we go around these, little tiny bit of weirdness in here, just a little tiny bit, but that's okay. You remember what sort of extrema this is? It's a maximum. Can we be more specific? Maybe not.
Let me see
I
what
have a
calc-
question.
I have an answer.
How come you did x1, x2, x3 not like in the wrong
Range.
like not numbers or something? You know, like never mind. Like why is it not negative?
She said no.
It could be negative. It's just x sub 1 is just -4 or whatever.
It's just
Doesn't matter. It could have been negative, but because we're just saying it's arbitrary x, we don't really have to. Okay. As a vocab reminder, this is bigger than all of its neighbors. In this, yep, this is a relative max. I call it a local max. Relative or local, they both work. This is bigger than all of its neighbors. Also a what? Global max. More so though, or relative, I'm cool with either. Is this bigger than every other y value? So not only is it a relative max, but it's also an absolute maximum or a global maximum. Does local and relative mins and maxes ring a bell? Okay.
I heard it.
How about absolute or global maximum? Absolute max?
does.
Okay. I like to call it global because we're just considering on everything, but I can call it absolute if you guys would prefer. This is bigger than all of its neighbors, right? Okay. Sweet. I don't think I need those definitions unless we probably should. Okay. Let's see. This guy right here is a local max. Okay. I'm going to give ourselves a definition over here. We're going to have a few more. By definition, we're going to say a local maximum has the following definition. If f of, don't laugh, we're going to use it, f of u, if f of u is greater than or equal to f of x for all x in an open, I'm going to say, for all x in an interval containing u, not containing, containing. Now let's really think about what this is saying. This is a local max, right?
Yeah.
Right here. Is there an interval around it that contains that x value?
No.
Why?
Oh. Yeah.
I can put an interval around it that contains it, right?
Uh-huh.
Okay. Is f of u, this point, bigger than f of anything else in that interval?
Yes.
This y value is higher than any of the neighboring y values. If that happens, like it just did, then f of u is a what?
It's a local maximum.
F of u is a local max.
What's the difference between a closed interval and open?
Open interval would have open points here. We don't touch them.
Oh, that's why you didn't put it.
Okay. Do we need to write out the definition for a local min?
No.
F of u is what compared to all x around it? Less than. Okay. Everybody cool with that? Now, as we're looking at this thing, it is a local max. It is. It's bigger than all of its neighbors. But there's more to it. Rather than just calling it local, what are we going to say? It's a global maximum. Let's define that one as well.
Of all points.
Yeah, not a whole lot has to change about our definition, does it?
I think I just look at it and all the rest of it.
If f of u is greater than or equal to f of x for which x values? For all x values. We don't have to say in an interval, just all x values. Then what is f of u?
A global maximum.
Perfect. Is a global max. Okay. Looking at my graph, there's a couple little weird things that we need to comment on. This point right here, is it an extrema? Why? It just stops. Based on this, it has to be an interval containing u, right? Can I put an interval around this part of the graph to contain it? I can see things on its right, but can I see things on the left of it? No, my function isn't defined there. Because I can only check on one side, would you call that a local max then? No, we have to have an interval containing it. I can't have an interval that starts over here and contains this point. This is not a local maximum. You have to have neighbors. Is this one a local min?
Yes.
Yeah, I have neighbors. Is this a local min? No. But hold on. Is it lower than every other x? So it's not a local min. It is a global min, though. So I'm going to sneak this in here. This guy is my global min. It's smaller than every other x. Not for globals. Globals don't care about neighbors. Relatives do.
Makes sense.
Yeah.
Like a neighborhood.
This f of u is less than f of x for all x. Like this is lower than every other f of x value on my graph. Okay. Everybody feel okay with that part? All right. Let's continue on. Crazy difficult? Feel okay?
It's okay.
All right. We get a theorem, I believe, right out of the gate here.
I don't know the first time I saw it.
I think we should probably just do some examples first, just to make sure we have it. Example. Okay, what I want us to do is, there's 4 parts to this, just so you know. State domain. I want us to determine where f is continuous. I'm just going to shorten that with determine continuity. I want to ID absolute extrema, or global extrema if you'd rather. We will use them interchangeably. And I want to ID relative extrema. All right, we get some graphs. Let's see what graphs we get. Ooh. I could give you graphs, or I can give you equations. Okay. All right. This first one is only in quadrants 1 and 2. Sorry, 1 and 4. What am I talking about? Okay, my function starts at this point. We'll call it 0, 1. Can you guys think of any functions that start there?
Y equals x plus 1.
Okay, there's infinitely many of them that start there. That was a poor question. All right, my next point is pi halves 0. Hey, we're getting tricky. My next one is pi negative 1. And my last point I want to talk about is 3 pi halves 0. 3 pi halves 0. I'm going to connect these with a smooth curve if possible. Is this sine or cosine? Cosine. 50% chance. Okay. Well, that's it. Almost. We'll call this function f of x.
Okay.
What is the domain of this function f?
Domain. Okay, so x such that.
0.
Can I just do an interval?
Yeah.
Okay. I'll even do really formal interval. X such that x is in which interval?
0 to 3 pi half.
Do I include 0?
Yes.
I heard both answers.
Yeah, because it's 0, 1.
It's filled in, right? It's defined here. I'll include it. 0 to where?
Comma 3 pi halves.
3 pi halves. Do y'all remember this symbol?
That is E.
The setup.
In the set of x such that x is in the set from 0 to 3 pi halves. All those numbers. It is. It's, there it is. That was my first little question. We'll star it. Is it continuous? Yeah. How can you show me with your hands? At the beginning of the year we did this. What's continuity?
Oh, wait, isn't there?
I like this more than this. I'm okay with this as well, as long as you're not like taking them apart. Limit's the same from both sides, and it's filled in. Lily, yours works well enough though.
Yeah, you could draw it up.
I don't have to pick up my pencil. Continuous on domain. Okay, no issues with continuity for this function. Okay. Are there any global extrema?
Yes.
Okay, global, what do you see?
0, 1.
Is that a max or a min?
That's a global maximum.
Global max happens at the point 0, 1. Is there a global min on this function?
Yeah.
Where?
Pi negative 1.
Okay, and I really want to specify here, we're going to talk about this as well. This is the ordered pairs where it happens, right?
Yeah.
What is the actual maximum value my function ever gets to?
0.
Which one's the values of my function, the x or the y? The y? Let me ask again. What's the actual biggest value? 1. And the smallest value?
Negative 1.
-1. Okay.
Also, we know the range.
We would. I didn't ask you about the range, but we would. Do you know the local min or local max?
Yes, the local, there's no local maximum.
There is no local max.
There's no local maximum, there's local minimum, which is also pi negative 1.
I'm going to say -1 this time.
Oh.
There is no local maximum. Why?
Because there's no neighbors on the maximum.
There's no neighborhood around it. What did you say? Okay.
Just look back in the recording.
All right. Shudula, yeah, it is the neighborhood, guarantee it. All right. Oh, we're almost to the cool part here. Oh, we got lots of time. Should we do a harder one?
Sure.
Good.
We're not doing derivatives anymore?
Oh, we will. Give it a minute.
Uh-oh.
All right.
That should have asked.
I mean, whether you asked or not, we were still going to do them.
Done in 2 minutes.
Friday.
Shh, God.
I'm well aware that it's Friday.
No one else said it.
Ooh.
Chanel too.
I like this one. Okay. Here we go. I get the point. My scale's going to be funny, but we're just going to trust the scale, okay?
Okay.
All right. I get this first point at 0, 1. And then this guy, downward parabolas to the point 1, 0. And then upward parabolas to an open 2, 1.
Touch the graph.
It's piecewise-y. Okay? And then we pick up at 2, 6 all the way up here with a closed point. And we run downward until we get to 6, -2. And we'll close out that one. Okay, this is a piecewise function. Huh. Okay, there are easy parts of these questions and hard parts. What is the easy part, you think?
Knowing if it's continuous or not.
That's one of them. There's another easy one.
Domain.
Domain, I think. Let's call this one G of X. So here we go. What is the domain of G? The set of X such that X is in, what's the first little piece?
Closed bracket.
Closed bracket?
0.
0 to,
Open bracket with a whatever that 2, 1,
all right, let's think.
which is 2.
You want this to be open, you want a parenthesis because it's here, right?
Yeah.
However, the domain only asks what x's do I plug in, right? I do not fill it in at this point.
Oh, because it's
However, is my function still defined right here?
yes.
Yeah.
Where?
Up there.
Oh. So that's really defined at that point still, and I keep going how far?
Until we go to
So you go to 6.
So I go to 6. My domain is fine.
But the continuity is not.
Continuity is not okay. I mean, it's okay. It's just it's not continuous. Where I love the language. Tristan says jump disco. Aldrin, where at?
At 2.
X equals 2. Love it. There is a jump discontinuity there. I don't need you to change your graph, but if this is what it looked like instead, what kind of discontinuity is it?
That is
Say it again.
removable.
Removable. Is that what you said? Nice job. Don't be shy. Even if you're wrong, I'm not, like, probably not going to yell too bad. Okay. Are there global extrema?
There is at 0, 1.
Gmax and Gmin. Let's find.
Oh wait, no, I was wrong. I was looking at the wrong.
Is there a global maximum here?
At 2, 6.
At 6. So I'm going to change the language again just so we can really start refining it. The maximum is actually 6 at which value? At x equals 2. Is there a global minimum of this thing? Yeah, where?
-2.
-2 at x equals 6. All right, this is the harder question. Local min, or max. I'll do max first and local min.
So the local maximum would be non-existent.
Okay, I want you guys to talk out the locals with your neighbors and see what you come up with. I'll give you like 30 seconds. This one I don't think is going to get anybody. Everybody can certainly agree there's a local min of 0 at x equals 1. Okay. The controversy might come from the second question.
It's removable, so it's not.
Okay. Here's the really important part. Can I draw a neighborhood of x values that I can plug in around that point?
No.
Of x values around this point?
Yes.
Yes. You're right. I cannot do the y. I agree. But can I check f of all of 2's neighbors on the left and the right?
Yeah.
Yes. Does that meet the requirements that we have in the definition? Let me check. In our definition, did we ever say so long as it's a continuous function?
No. Okay. So
No, I can pick x's that are on either side of it.
Awesome.
With that said, do I have a local max?
6 at 2.
It's 6 at x equal 2. I have a maximum because I can check f of all of its nearest, dearest neighbors.
I guess
It's
0,
an apartment
1.
complex, so there's just subdivision.
Why is this not a local max, Jadri? Can you check its friends on the right?
Yeah.
Can you check its friends on the left?
Oh. No.
That's it. No, can't do it. All right. We get one theorem really quick. Okay, here we go. Theorem. This is going to be redundant, but I want it to look nice in your notes.
If it's redundant.
We're going to talk about the extreme value theorem. The extreme value theorem. Okay, super easy to write this down. I think it's super easy to make sense of. Here it is. If f, can I say is continuous, and you guys know I'm talking about a function? If f is continuous on some closed interval a to b, so imagine any two x values. If you can draw it without picking up your pencil, we guarantee then f has an absolute max. I'm going to call it abs max and abs min. If your function is continuous on a closed interval, they're guaranteed as an absolute max and absolute min. There's one little weird situation where they'd all be the same, a horizontal line. Everything's an absolute max and everything's an absolute min. I won't give you that question. It's just, it's uninteresting, it's odd. Okay, now, I don't need you guys to draw this. All I need you to tell me is from A to B. I just want to think about these. Does this function have an absolute max and an absolute min from A to B? Yeah. Global. Yes. Absolute global. Absolute max. Absolute min. Okay. How about a function that gets all crazy and does something like this? And then it comes out like this.
It does.
Yes, it will also have. How about this one?
It's not continuous on A through B, so no. Now it is.
Is continuous?
No.
Okay. Now, here's the important part. This is not continuous. Does this theorem apply then? No, it's not continuous. I don't care about this theorem. Does it still have a global max? Yeah. Does it have a local max?
Yes.
Can you pick x's on either side?
Yes.
It's still a local max as well, but you can't guarantee that it will exist. Okay, has to be continuous. All right, we're going to build some intuition. I think that's where we're going to leave off. Okay,
We keep this.
You know the intuition
we're going to do it in a picture, so I want you to draw these. Okay,
Is it intuition challenge on TikTok where you like close your eyes and then you just tap?
okay, I want us to consider the following function. I'm just going to sketch a function that has mins and maxes. We're not doing any more problems, but we're going to see how this relates to the calculus. I want you to draw this. Yep. Yours does not have to look identical to mine. I'm not even going to have a scale. I'm only simply going to make sure that I have a couple weird things going on. I'm only going to work from A to B. So let's say it starts up here, does something like this, and then has a sharp turn and comes downward like this to there. It is, love it. It's continuous, but it's not differentiable at that point. I agree completely. Okay. I'm going to call that A, and I'm going to call this B. Do you guys see a local max, or even a global max?
Yes.
Okay. It's about right here, right?
Probably.
All right. Here's the calculusy part of this. Let's imagine that we have tangent lines moving towards that point. You cannot sketch all these, but I can. Okay, that's a tangent line, right?
Yeah.
Okay, it's right there. Then the closer I get, what's happening to that tangent line slope?
It gets smaller.
Give me another name for the slope of the tangent line.
Zero.
The derivative. What do you think the derivative is right here? Okay. Huh. Will that always happen if it's a max like that?
Yeah.
Ooh, I'm glad I asked that.
Unless.
What about here?
Yes.
Derivative is 0 still, right?
Yeah. Well, right there it's undefined.
Jadri, go ahead.
I don't know what I'm saying.
It's natural you want to say if it's a max, the derivative is 0. Here's the issue. Is this a maximum?
Yes. But the derivative is not defined.
It's not differentiable. So, last little thing we're going to write. At our extrema, and this is just an observation. At local extrema, f prime is either,
Good afternoon, everybody.
we're going to wait for him.
We have a lost phone in the office, so if
It's
you
mine.
lost your phone, please go and swing on by. A reminder, the talent show is tonight at 6 o'clock, and for anybody in danger of the grades, remember that Saturday academic lab
All my grades up to
is
Tuesday.
and Mr. Carroll, be sure to be safe out there. The roads are slippery.
At local extrema, f prime is,
Who's this?
Next week is the last week to vote.
middle schooler.
If I can't, It is held in room number 39. So if you're participating,
Oh yeah, one more thing.
F prime is either 0 or what's the other possibility, Lily? Undefined. We will, what did you say the first time? Okay, not differentiable. I'd be okay with that. Okay, I would encourage you, if you think you need more practice with related rates, look over a couple this weekend.
Okay.
We can do them at the start on Monday, but you got to bring them to me. No, we did it all. All right. Thank you guys. Appreciate you.